Hello, everybody, and welcome to another Bitcoin review club. And so today we are going to review PR number 17526, which is quite an old PR and it already got merged, but it gives us a good look inside the coin selection algorithm of Bitcoin Core. So it would be pretty fun, and hope people just glance through the notes and the questions. We will this time we'll like not dive too much deep into the code, though we'll see some of the code snippets where the coin selection few key logics happen, but mostly we'll try to revolve around the concept and the understanding of coin selections, output groups, effective values, and things like that. So with that, let's get started with our questions and usuals. So the first question is about a high level description of coin selection strategy and what this PR tries to do. So can anyone summarize like what is coin selection? Let's just start with coin selection. What does it mean by coin selection?
I mean, it's just like you want to select the UTXOs that you want to use in a certain transaction.
Right. So a wallet has a bunch of UTXOs. That's wallet's job. They basically are UTXO maintainer, and so whenever we are creating a transaction, we need to select some inputs to fund that transaction. And the question is, how do we select one? If there is like 100 UTXOs available in the wallet database, which one do we select? What is the strategy? What is a best selection? What is a worst selection? So all this kind of like logic and selection mechanism of like selecting the UTXOs to create the transaction is part of the coin selection. So that's coin selection. So what does this PR do? So what is this PR's trying to change there?
So like this PR adds a new point selection called single random draw.
Mm-hmm. Right. So it adds a new coin selection algorithm to the set of coin selection algorithms that were already in Bitcoin Core, and that's the basic change of this PR. So if we go and check out the files changed, and all the coin selection logic and its associated structures are defined inside source wallet coinselection.cpp and inside coinselection.h. So inside coinselection.cpp, this guy adds a new function called single random draw. And single random draw is like nothing other than randomly selecting from the UTXO one by one until the target value is matched. So if we look at the code of this guy, coin selection CPP, approximate base subset, knapsack, select coins SRD. SRD stands for single random draw, and you guys can see like it's a pretty straightforward and simple patch of code that basically takes the UTXO set and shuffles all the UTXO indexes together and runs a for loop for each index, get the output value. If the output value is and put the output value inside this value return, and if the value return uh, greater than target value, so there are two variables where the output value is being referred: selected effective value and selected value return. We'll talk about effective value a bit later. So the logic here is, if the selected effective value after checking it randomly gets greater than target value, then throw out that particular result. If no such UTXOs are found, which even like all the sum of the UTXOs doesn't fit to the target value, then we return a standard null option. So in this part of the code where they define SRD, and then and this is coinselection.h, in spent.cpp, where the coin selection is actually happening, this is inside attempt selection function. They add a new algorithm inside the function. So attempt selection is basically the function that tries to do the coin selection on a given transaction heuristic. So spend.h select coins, and this part of the code got recently like added by this PR. So previously we only had up till this part, right? So previously the selection process was like select coin BNB. If BNB select coin is success, then we add the result. If it's not a success, then try a knapsack solver. If knapsack solver is a success, we add into the result. And if that's not an success, then we select coin SRD. We randomly try to select with single random draws until the value hits the target value. So that's the main addition of this particular PR. And the this function kind of like defines the workflow of course coin selection algorithm. And there is also a nuance to it, is like if BNB succeeds, then we will basically not try knapsack solver and select coin SRD. And if it doesn't succeed, then both knapsack solver and select coin SRDs are done. And depending on the value of that result, so this part of the code basically compares the result between knapsack solution and SRD solution, and whatever gives us better solution given some heuristic, this part of the code is the heuristic of the choice. So this is the heuristic that basically tells us which one is better and which one is worse. And as per these heuristics, we compared the two results of the two algorithm, knapsack solver and SRD, and whatever is the better up to these heuristics, we throw that out as a best result. But we only do that when BNB fails, right? So this is kind of like the gist and the heart of the coin selection algorithm of Bitcoin Core. Viewers can also go and check the definitions and the implementations of knapsack solver, BNBs, and SRD. SRD we just checked, it's pretty straightforward. Knapsack and BNB is a bit involved. So, and this part of the code, like select coin, is basically all the auxiliary thing that we do before getting the attempt selection. So the select coin basically calls attempt selection with multiple coin eligibility filters. We'll talk about coin eligibility filters a bit later, but select coin is basically tries a various form of attempt selection attempts. And attempt selection is like the same process. Try with BNB, if not knapsack SRD, whatever is the best, that's our result. So yep, that's the approach and the changes. Any questions so far on this?
Yeah, I had a quick question on the performance, right? So the worst case scenario, you might have to call like all algorithms one upon the other. So what's like the performance differential? How much time does it take? I'm assuming it's like a few milliseconds for each, huh?
Yeah, I'm not exactly sure on the numbers on what exactly how much time does each one of them takes. My understanding would say like BNB would be a bit slower, and knapsack solver, even knapsack solver could be slower than BNB given the input set. So knapsack solver is also a subset sum solving technique. BNB, branch and bound, is also another subset sum solving technique. And I might be wrong, but I think like knapsack in given situations could take even higher than BNB, but BNB generally would take more. SRD probably would take the least amount of time. But yeah, given like that, it depends on your UTXO set in the wallet. So this goes into the conversation of the UTXO set, like what kind of UTXO set the wallet should maintain so that it coin selection algorithms easily find solutions out of it. So, but I don't know the exact numbers.
Okay.
Yeah, I'd like to say something. And if I'm not mistaken, I think like all three coin selections run together. Like we don't only run knapsack solver and single random draw. if BNB fails. Like there are cases when BNB can produce worse solutions than knapsack or single random draw.
Oh, so they
Okay.
run together and then we compare like from the effective value or something.
Yeah,
Yeah,
basically, and then we will also compare like if this is, yeah, I think this is the comparison that is going on, and this guy is saying like so result begin, result end, minimum element, and it's saying like so the result is a structure that is an amount and input coin and another amount, so it's a tuple of amount with standard and C amount. Some is the target value, and one amount is the fee. And okay, make tuple BNB value. So this is the west. So the first index of the tuple is west. The second index of the tuple is the total value selected by the algorithm. So here is saying like whoever is the least waste. So there is a way of calculating waste on a selection result, and whoever has the least waste, or waste is equal and the size number of, so this one is like standard move BNB coin. So this is a set of coins that are being selected, the index number 1. So whichever has the least number of inputs selected, we choose that guy if the waste is equal. So um but I thought like BNB always sucks. Like if BNB succeeds, we don't do knapsack and SRD. I also thought like I read that somewhere. Let me check. Probably it was in the
well,
notes.
yeah, not exactly. Like imagine a case that BNB produces, like there are 1000 UTXOs and there is one UTXO which can spend the same amount. So BNB will try to create a changeless solution. So it
Mm-hmm.
will select those 1000 UTXOs,
Mm-hmm.
and knapsack solver or single random draw would just select that one UTXO and produce a changed output. So in high period environments, it would be beneficial to spend that one UTXO and create a change output. And in low period
Right.
environment, it would be
I understand
like
that
that.
logic, but is it implemented in code in that way? Like
Yes.
mm-hmm.
So if you see the code, then we are calling select points BNB, and if it succeeds, we are
Putting the
adding the
results,
one.
place back the
Yeah,
result into the result vector, and then we are
and
following. Hmm.
then we are also running knapsack solver and single random draw.
Makes sense. So why did I rate it like this? Uh, so here's the line, right? So there is a clear preference for BNB, and we will only try knapsack and SRD if that fails. However, we will try both knapsack and SRD together and picking the whatever is the best solution. So I guess that's not true anymore.
Yeah, maybe like they initially implemented it that way and then
But now
changed
they
it later.
changed, and now
Yeah.
yeah. So yeah, BNB will also have situations where it will not find any solutions, and sometimes it will find worse solution. And yeah, it heavily depends on what is the UTXO set you have in your wallet, right?
Yeah.
That makes sense. Yep. So yeah, from the implementation right now, it's also, I have checked out the PR branch which was merged. So even at that point it seems like, yeah, I was also confused with this part of the code. It doesn't seem like returning after this, right? It's
Yeah.
also like doing all these steps even BNB succeeds, right? And okay. Okay, that makes sense. So this algorithm is not on top of knapsack and SRD only. This is also like comparing the all the three selections together, and whatever is the best, uh, we go by that.
Yes.
Cool, cool. Okay, let's move on to the next one. within select coins minimum conf, we have both a knapsack and SRD solution. How do you decide which one to use? I think like the select coin minimum conf, it was the name of this function, which was later changed into attempt selection basically, because select coins is basically doing the same thing, select coins minimum conf with coin eligibility filter, and now it's doing the same thing with this function called attempt selection. So I think they are the same thing that they are talking about, so we can like directly translate the question for attempt selection. And the question here is, within this, if we have both have knapsack and SRD, how do we decide on which one to use? We kind of like answered it, right? This is the heuristics that they choose. First, get by west. If west is equal, then get by the lowest number of inputs selected. And I think like that's also like fits to the point that you said, like if there are like 1,000 UTXOs that makes up one transaction and there is like one UTXOs that could have covered it, knapsack would have picked it, but BNB might have chose those 1,000. So here it will get caught, right, in the number of size of inputs. And so that's how we are choosing between which one to use. Yeah. Any other question at this point on this choosing and any other thing? Okay, we'll move on. So this is another like coin selection philosophy question. Why might we prefer to spend more inputs in the same transaction? Guesses? I think there are multiple reasons why we want to do that.
I mean, we have to eventually spend every UTXO. So if we are in a low fee rate environment and spending is cheap, so we might choose to spend more inputs in a transaction.
Yeah.
Plus, we want to reduce the UTXO set, right?
You also want to reduce the UTXO set on the global Bitcoin network, because that's a burden on every node operators, right? Not only they have to store the blockchain, they also have to store the UTXO set, right? But on the other hand, if you consolidate your UTXOs too much, you might have you might find difficult to have changeless solutions, right? Because if your UTXO values are not distributed in a well distributed way, if like you have like only few chunks of very big UTXOs, then your BNB never succeeds, and you will always end up having change solutions. So this is like a very big open question right now for wallet engineering, and there is no one good answer, because it depends on usage to usage. For example, a user using his wallet in mobile will prefer certain kind of distribution of UTXOs, where an exchange wallet will prefer certain other kind of the UTXO distributions. So it's a very nuanced and situation specific topic. So that's why like there is no one single way of doing it. Core probably does the best on this term, doing all the three solutions and trying to find the best with some heuristics. But many wallets out there just uses some, either they go by knapsack blindly, or they go by combinations of FIFO, LIFO, SRD, and those kind of stuffs. Anybody has seen any specific interesting coin selection algorithms out there that caught eyes, or any other algorithm people, like sequence of algorithms people are aware of that used somewhere else?
Well, in Bitcoin, we have another coin selection algorithm that's not in code. It's called lowest larger. And yeah,
Right.
We combine binary search with greedy approach to select coins.
Right. Yep. That's a very cool one, and hopefully we'll have the video out soon. We recorded with Anmol on the details of lowest larger, and yep, that's something that is that is probably new, and would be good to have like multiple implementations of the logic into different language so other wallets can use it. Like I'll be definitely interested to get it into BTK someday in some form.
Yeah.
Okay. Any more questions? So here's another question that doesn't actually got touched into the list of question is like, what are the preferences of coin selections and how they are self-conflicting with each other, right? So but trying to optimize on one thing reduces optimization on another thing. And anyone want to elaborate on that if somebody have some idea?
I mean, you wanna reduce the
Yeah,
fee
I can
that
go like
Yeah, go ahead.
Anmol, go ahead. You probably have a better idea than me.
I
I
think
mean,
he is not
yeah.
Anmol.
So no, it's me.
Oh, you joined.
Yeah.
Okay, I missed you. Sorry, bro.
Yeah, no worries.
Okay,
Yeah.
okay.
So
Yeah.
like as I was saying, like you have to pay more fees to get your transaction confirmed faster, but you also don't want to pay too much fees
Mm-hmm. Yeah.
because yeah, you want to do fee saving. So that's one of the conflicting rules.
Yeah. And then also like you wanna consolidate UTXOs, but maybe not too much
Yeah,
because that reduces like efficiency of your selection, but you also don't want to increase the burden on the Bitcoin network. And also there are like some privacy concerns of it, right?
yeah,
If the wallet doesn't randomize certain things in certain ways, then that can be used as a fingerprint by chain analysis and people like that. Okay. Moving on to the next one. This one is a bit interesting, and it's basically kind of like a code question, and it says like, based on the coin selection scheme proposed here, let's say that solution A, B, and C exist. Ignore the fact that we exit early by finding a solution we're satisfied with. But let's say like there are three multiple parallel solutions. We can choose any one of them. And which one would we pick? And which one would we pick? So solution A is picked by Knapsack, produces a change output, pays 100 sats as fees, and only uses confirmed UTXOs, each with 4 confirmations, right? So this is like a selection that produces a change, thousands, 100 sats in fees, all inputs have 4 confirmation. Solution B picked by BNB, no change, pays 95 in fees and use one unconfirmed change output. And so here the change, there is no change. The fee is 95 sats and one unconfirmed change output. So one unconfirmed change output. Okay, one unconfirmed change output means like one unconfirmed output from our own wallet. So it's a trusted unconfirmed output, right? And the last one is picked by SRD, produces a change output, pays 99 sats in fees, and only uses confirm UTXOs with each confirmation. And the hint basically says like, go look into the attempt selection. Go look into the select coin function and try to figure out from which part of this various coin eligibility filter the solutions will come up. And probably each one of those solutions will come up from different combination, like each combinations of this coin eligibility filter. So can anyone help us go through which one will be selected first? So for example, whatever is satisfied by this guy will be selected first. So let's just see if it's get satisfied by this guy. And coin eligibility filter says like, these are the 3 parameters. It says like, so first one is confirmation of mine, second one is confirmation of theirs, and third one is max ancestors of of the input. So confirmation mine means like if I have a change output, so my wallet identifies that change as an output that is generated by my wallet, so nobody else can like spend it out or something. So that's a trusted and it's called mine. So eligibility is like mine will require one confirmation, and confirmation there is like if that's an input, that if that's an output that came from somebody else, it means like I gave an address to somebody and somebody paid to that output, so it's those are identified as theirs. So change is mine, receive is theirs. So if we try to select and receive, we need to have 6 confirmation. And max ancestor count is like if we are doing unconfirmed transaction, how many ancestors are there in the mempool. So the first one was knapsack, pays 100, uses confirmed UTXOs each with 4 confirmation. So that basically satisfies this guy, right? So that will pass the coin eligibility filter was 1 confirmation ours, 6 confirmation theirs. Oh, low. So if among the 4 UTXOs only uses confirmed UTXOs with each 4 confirmations, so that is not a full amount of information, because if any of the UTXOs is theirs, so that will not pass through this 6, right? What do you guys think?
I think the best guess would be second filter, like 1 confirmation for our
The
output and
BNB?
1 confirmation. No. Can
Oh,
you change your screen?
oh, sorry. Yep.
So yeah, here, so I think line 501 would be my guess, because it has 1 confirmation for our output, 1 confirmation
For
for
their output. So
yeah.
none of the options here will actually pass line number, like the first criteria, right?
Yep.
Right. So the second criteria has 1 ours, 1 theirs, and 0 ancestors. So let's see. This guy should pass 1 ours, 1 theirs. Right. And use 1 unconfirmed change output. So this guy will not pass 1 ours, 1 theirs. And SRD uses confirmed UTXOs, which each with 1 confirmation. So this guy will also pass 1 ours, 1 theirs. Does that make sense?
Yep.
Right. So in the second part, so in this line, none of the selection will pass, right? And in this line, both this guy and this guy will pass, right? And but I do have a feeling like this has to be the better solution. But it uses one unconfirmed change.
But because change belongs to us, so we can't spend it.
True. Yeah, change is trusted, so we can spend it. And given the ancestor count is like not too large. And so let's just go through, because this part of the code I found a bit interesting, is like what happens when 0 ancestor things fails, and what happens when we go into the unconfirmed selection zone. So here we are saying like this is the first one that tries, like ours is unconfirmed, theirs is 1 confirmation, but in that case we have a maximum ancestor count of 2. If our unconfirmed has more than 2 ancestor count, then we don't try it. If that fails, then we do this minimum of 4 and max ancestors by 3. So max ancestors is probably a policy level variable that is there in mempool. I don't know where it's coming from. It's coming from this, and limit ancestor count, and limit ancestor count is 0. So I guess, so max ancestor count by 3. So max ancestor count should be 1 at this stage. and max descendant count is also coming from that limit descendant count. Is it being changed somewhere, like updated, addition? Like we start with 1 and divide by 3, that's it. Interesting. Okay, then we reduce by 1 later on, so we fall back to 0.
I think like max ancestor and max descendants are mempool properties, which I don't know why they've set it to 0, but if I remember correctly, like the maximum number of transaction chains which you can have by the default settings is 25. So I think that we are using that here for max ancestor. So you can like by the default settings, mempool will allow chains up to 25 transactions.
Should be, but now I got blown by this line.
Yeah.
It's defining it as a max of this guy and 1, and this guy is set to 0, and it, oh, something is happening here. Get package limits. Oh, this is where the package limits is coming. This is the mempool.
Yep.
Right, so the nodes package limit, and this is the mempool package policy. So max ancestor and descendant count are getting there, and this is max ancestor is the max of 1 or this guy, right? So
Yeah.
so then we try with a minimum of 4 or max ancestor descendant by 3. If that fails, then we try max ancestor by 2 and descendant by 2. If that fails, we reduce it by 1. Then if that fails, we take all the unconfirmed transaction, even their UTXOs we consider as unconfirmed, and we reduce by 1. And what happens after that? So if that fails, then we go unbounded and in the descendant and ancestor count. But this is also gonna get bounded by the ancestor descendant count in mempool, and that's the doc here over here. Try with unlimited ancestor descendants. The transaction will still need to meet the mempool ancestor descendant policy to be accepted to mempool and be broadcasted. But outgroups use heuristics that may overestimate ancestor descendant counts. Okay, so even if you are going numeric max, it doesn't mean like it will create a valid transaction. It might still get blocked by mempool ancestor descendant count. Yep. Any question and discussion at this point on this part of the code? So we didn't answer the question and the file. Which one is the best? Which one do you guys think is the best solution? Unconfirmed change with no change and lowest amount of waste seems like a good candidate. Solution B.
Yeah, like
only if the
But-
unconfirmed is like your own input.
Yeah, go ahead, Anmol.
yeah, I was saying like we don't have the number of inputs given here, so we can't really say. But if we just go by minimum fees, I think BNB would be the best.
Yeah. Which one do you think is the worst?
I can't really say because there's no
Not
because we
enough
don't know
data.
the number of inputs.
Right.
Yeah.
Unconfirmed. It just says unconfirmed UTXOs. It doesn't say how many. Yeah.
No, the number of inputs which we're using, we don't have. So what if the BNB has 1,000 inputs and knapsack has only 1 input? So I prefer
Right.
using knapsack.
Yeah. But
So we
but
don't
that
have-
kind of like tells us about the fees, like total fees paid, right? So definitely the size of this guy is smaller than the size of this guy.
Oh yeah. I totally missed that. Yeah, so like BNB is just better because it produces no change output and pays less fee.
Yeah. And the worst is probably tie between A and C. Uses confirmed UTXOs with each one confirmation, 99 fees, and 100 fees with confirmed UTXOs with 4 confirmation. Seems like almost similar size of transaction, more confirmation and less confirmation. So just on that heuristic, I'm going with A is better than C, so probably C is the worst.
Yeah.
Cool. Nice. Okay. If not any other comments or questions on this, we'll move on. So the next one is, what are output groups and why does SID pick from output groups rather than UTXOs? Yeah, that's a good question. So what are output groups? Let's just open output group over here. So this is a structure that's inside source wallet coinselection.h. Let's try to open it up over here. Coinselection.h. And we have this structure that is used many places wherever coin selection algorithms are used is output group, basically a group of UTXOs paid to the same output scripts. Oh, that gives out the answer. So anyone want to chime on like why do we want to do output groups? So each output group is basically a group of UTXOs that has the same addresses. So it's basically address reuse, all the UTXOs grouped together who have address reuse. Why do we want to do that?
So like for preserving privacy, we might want to do that because, for example, if I have two UTXOs which are paid to the same output and I like make two different transactions using that, so like chain analysts can know that these both transactions are made by the same person.
Right. Yeah.
So that's why we want to try to spend the UTXOs paid to the same address together.
Yeah. Yeah.
But that can be the norm, right? So let's say if the number of UTXOs are not enough or the effective value is not enough, then you might have to choose like some UTXOs from the other output group as well.
Yeah, you will do.
Okay.
As long as we spend the outputs to the same address together, we don't lose any privacy.
So there is a flag that is like allow partial spends or something like that. That basically that basically don't circumvent this logic. But the point of having an output group or a group of output is like whenever we have address reuse, we wanna spend all the UTXOs of same addresses together, even if we are outshooting the target value. And we want to do that because if there are address reuses, if there are cases of address reuse, we want to minimize that as soon as possible. So if there is a situation like there are 10 UTXOs, 3 of them are of same output, rest are all same address, rest are all different addresses, and one of the UTXO of those three UTXOs got selected in the selection algorithm. So the remaining 2 will also get selected, even if the target is matched, because we don't want to lie around, we don't want to keep around those reused addresses in the UTXO set, because that leaks our balance all the time. So
makes sense.
So that's what output group is. And the next part of the question is, why does SRD pick from output groups rather than from UTXOs? And so single random draw is the concept of like randomly selecting from the list of things. Why output groups rather than UTXOs?
I mean, I think we already answered that because like for privacy.
Yeah, because SRD can randomly choose, SID will randomly choose output groups, but if it randomly chooses UTXOs, then it might not cover all the reused and put them together. Yeah, that's the answer.
Yeah.
Any questions on output groups? Okay, so we move on to the next one. And this one is about, this is where we go into the concept of effective values. So what does calling group output with positive only equals to true does in SRD? And what could this is the first part. What could happen if select coins SRD was called with all groups instead of positive groups? Okay, we'll answer part by part. What does calling group outputs with positive only equals to true? Let's just find group outputs wherever that function is. And it's inside spend.cpp. And if you go to the definition, the group output is basically saying like it creates a vector of output groups. So it gets a wallet, gets all the UTXOs of the wallet, takes some coin selection parameters, takes a coin eligibility filter, and takes a Boolean flag positive only, true or false. And depending on that, it spits out a list of output groups. And output groups are the same thing that we talked about. And the question over here is, what happens when positive only is true? So let's just see. So positive only is used over here. If positive only and group get selection amount less than 0, continue. So check the output group's eligibility and only add eligible one. So what this guy is basically doing is saying like, if positive only flag is set, only take the UTXOs or only consider the groups which has a positive effective value. And now comes to the question, what is an effective value? So anyone want to chime on what is an effective value?
That's the sats in a UTXO minus the fee.
Fee of what? Almost close.
Of spending that UTXO.
Yeah, the fee of spending that UTXOs in future. And now the question is, how do you know the fee of spending that UTXO in future?
That's a good question.
Yeah.
Because the fee rate might change, with time.
Yeah, fee rate is always changing. So, Anmol?
Yeah, so like not the fee rate of future, but for calculating effective values, we use the current fee rate.
But there is a long-term fee rate that also.
There is a long-term fee rate that is used to calculate waste.
Oh, right. Yeah, that is used to calculate waste. So for calculating the effective value, we try to we calculate it via the current fee rate that is going on in the mempool.
Yep.
Right. And the effective value is basically the effective value is the value of the UTXO minus the fees required to spend that UTXO. So positive only means like positive.
One second, right? So wouldn't the output or the calculation vary within like a few minutes? Because sometimes it's like the fee for a certain block is 25 sats or 30 sats. And then the next block is 3 sats, 2 sats. It's like 1/10 of the previous block. So wouldn't that change the calculation within a few minutes?
It will, but I think it tries to do an average of certain previous blocks. I'm not exactly sure. I don't know the details of it. So it will change in theory for each block and each instant of time, depending on the situation of the mempool, it will continuously change. But it probably has an heuristic to catch on a value, and you just you also need it at the time of sending a transaction. So sending a transaction is a very instantaneous thing. So you don't have to keep calculating the effective values of groups all the time. You only do it at the moment of sending a transaction. So whatever is the fee rate at the moment of sending a transaction, you can just go ahead with that. But by the time you broadcast that transaction, the fee rate might actually change.
True.
Right. So here by positive only, it basically says select only those groups which has positive effective value, and groups or UTXOs with negative effective value basically means it's gonna cost more to spend that UTXOs than the value of that UTXO. And so we basically never want in our wallet a UTXO with negative effective value. And even if it gets negative, I don't know exactly what core does, but probably it's better not to spend them, because you are going to lose fund by spending those UTXOs, and wait for low fee period time so you can consolidate all those effective UTX, or like negative effective UTXOs together in a very low fee rate and put it in a single UTXO. Any other thing we can do, Anmol? You have any pointer like we can do to handle negative effective value coins?
Yeah, like there's no benefit of spending uh, coins with negative effective value unless you want to waste your money.
Yeah,
So
so in a sense, like coins with negative effective values are kind of like forever blobs on the UTXO set.
yeah, I
Hmm.
mean you can technically remove it, but there's no like unless for collective good you want to pay the fees and just consolidate them into one UTXO. But yeah, there's no obvious benefit of doing that.
Right. Yeah. So and in a case like what happens when a wallet uh, so what happens when a wallet encounters a change which has negative effective value? It just puts it back into fees, right? At least the
I
core
mean,
does it.
yeah, so like we try avoiding very small, making a very small change output. So we can just throw, so there's something called cost of change, which is
Mm-hmm.
used in base metric. So
Mm-hmm.
we use that. So that is actually the cost of creating and spending that change versus the cost of throwing the excess amount to the fees. So like whichever is better, we do that. If it's
Okay.
beneficial to create change, like for example, the cost of creating and spending change in future is 5 500 sats and the excess selection amount is 1000. So we would actually prefer creating a change. I
Hmm.
mean, this is not a good example, but yeah, that's how the logic works.
Okay. Okay. Makes sense. Um, okay. Any other questions, pointers on output grouping, effective values?
You can move to the next one.
Mhm. Okay. And the next one, or the second part of the question, is what could happen if select coin SRD was called with all groups instead of positive groups? So let's just go select coin SRD. Um, I think this is inside coinselection.cpp, select coin SRD. And we have output groups with UTXO pool. We already gave an output group with UTXO pool. So spend.cpp, where this guy gets called, attempt selection, uh, select coin SRD, positive groups. And positive groups are calculated group output coin selection parameter eligibility true. We only select positive only. So it seems to me like probably okay, positive group also select used for BNB. Positive group doesn't need to be there in knapsack. And select coin SRD also uses positive group. So what happens? So uh, it seems like code always prefers positive only groups except for KnapsackSolver. So
Yep.
knapsack can also include negative effective value groups. Oh, here's the all group. And all group is by group outputs with positive only equals to false. So knapsack is run over all groups, and BNB and SRD is run over positive groups. Now the question is, what happens when BNB and SRD runs over negative group, like all groups? Even I don't know. Anybody have any
So
idea?
like you may end up spending like uh, can you show the code?
Here. Uh, which one?
No, the select coins SRD.
Select coin SRD. Okay. Here.
Yeah, assume group selection amount is greater than 0.
I think that comes from that fact that we always have positive values in the group.
So I think it will just error out here
It
if it's
error
less
out
than
here
0.
on this, so it works with the assumption that we only working with positive group. But theoretically, what's the like problem of like having negative
But
there?
yeah, you will end up spending those. You'll end up paying extra fee.
Hmm.
That's it. You'll just select those output group.
Hmm. Right. Mm-hmm. Makes sense. And so does BNB also has this assumption in the code? Um, doesn't seem like, should be somewhere very start if there was an assumption. Is
Well,
the-
it should happen when we are selecting that output. So it should be somewhere inside the for loop. Just scroll down a bit.
No, it doesn't have that assumption.
Okay. Yeah.
Okay. But it's always get called with positive groups. So, but here it's probably used as a precautionary, because also like select SRD is also called only once in attempt selection with positive group.
Well, yeah, we don't need it in BNB because when BNB runs, we sort all points by values. So even if we have negative effective values, they'll be at the end, and BNB would probably never reach that.
Okay. That makes sense. But SRD is like random beast,
Yeah,
so it can go anywhere.
yeah.
Okay. Cool. Yep. That's a valid point and that makes sense. Okay. I think that answers the next that part of the question. Um Okay, so what are some ways of deterministic coin selection? The seventh question we are answering. What are some ways of deterministic coin selection algorithm might leak information about wallet UTXO pool? Why do we shuffle Vcoin, vector of coins before creating output groups? So yeah, so the first part of the question is, what are some ways a deterministic coin selection algorithm might leak information about the wallet's UTXO pool? Pretty interesting question and could be a lot have nuance into it. Anmol, you have a take on this?
I mean, uh, one of the obvious issues is that, for example, if a wallet uses oldest first, so we can know just by looking at the transaction produced by those wallet that the
Hmm.
UTXOs that they're spending are oldest first, or if they go by newest first, like
Right.
so just any algorithm that sorts them by age, we will know.
Yeah. So if we can identify the address of that transaction that coming from this particular type of wallet, and if we know their algorithm, which is deterministic in nature, we
Yeah,
can have some profile about the funds of the user of that wallet. Is like if
yeah,
that's the biggest fund the user wallet has, or if that's the first one that came into user's wallet, and all these kind of things. And and that's probably the same reason we shuffle vcoin before creating output groups. I think that part of the code should be uh coin selection.h output groups, coin selection.cpp out. Where do we create output groups?
I think it was a function called group outputs.
Yeah.
You have it open in the search bar on the left side.
Yep, stupid me. Group outputs, and it takes a C output, a vector of C output, and it randomizes it somewhere. Can't seem to find it in a easy way. Let's search for Bitcoin. Bitcoin is there in select coins, and nowhere after that, and attempt selection, then group outputs. Is there a vcoin somewhere here? Probably this part of the code changed a lot after the
Yeah,
PR. So
probably.
so where exactly is vcoins are being shuffled? Should be shuffled somewhere while creating the group. So these are my
Maybe
outputs.
maybe the output groups are already shuffled when we call group outputs.
Yeah, could be. And it should be there in positive groups with group outputs. And these are the coins. And the coins are coming from the vector of C output on attempt selection. And attempt selection is having here. So attempt selection is being used here. So this is the vector of coins. And here's the shuffling
Yeah.
is happening. Right. And
Yeah.
Right. So this is like attempt selection is working on UTXOs. I'm getting a bit confused here. So these are UTXOs. These are not groups, right? So these are
Yeah.
UTXOs. C outputs. Attempt selection is using that, and then attempt selection is using that. Select coins is over there. Who is using group? Now I'm confused. Like, who is using the groups?
So attempt selection is making the groups and then calling the coin selection algorithm.
Right. Attempt selection is creating the groups and calling the, okay. So before calling attempt selection, we shuffle the coins and then call group outputs on them.
Yeah.
So this basically changes the sequence of the outputs inside a single group, right? So
Yeah.
if group 1 has 1, 2, 3, in the next one it might have 3, 2, 1 or 2, 3,
Yeah.
1 or something like that. The same group doesn't always have the same sequence of coins.
Yeah.
And that's like extra part of randomization.
Yeah. Exactly.
Yeah, makes sense. Any questions so far? Okay, we are almost at the end of our time, and we have a bonus. We have listed some qualitative presence of change output and quantitative number of inputs used, ways to compare the coin selection solutions, that heuristics that we talked about. Instead of returning as soon as coin selection minimum conformation find a solution, should we try multiple and then pick one? How might we design a metric to decide which one to use? And I think like this is the question which was there when West metric wasn't designed. And
Yeah.
the answer to this question is basically the West metric. So let us just go through that part of the code once more. And
I think like when base metric was added, it's then that they decided to run all coin selection. Maybe previously they only ran BNB, and if it returned an output, then we don't run an knapsack and SingleRandomDraw.
right.
But with base selection, we can try all that.
So that's what the previous point was like here.
Yeah.
That's why they said it over here that previously they don't do it. And now this is the answer. Basically like they do multiple times and they have a West metric, and West metric is the heuristics that we use to find what is good and what is bad solution. And we compare all of them, and whatever is the best, we choose that. And if West metric fails, we go by the number of inputs. What happens if that also ties up? I think it goes by the fees after that, right? Or something like that. I don't know, making it up, but it seems like if there is a tie over here, then randomly one of them will get chosen.
Yeah, like I think BNB would the first result in the best result vector is BNB. So
Mm-hmm. Yeah. Yeah. Right. If there is a tie, whichever is the first one, they will probably choose that.
yeah, but yeah, the chances of tie are very low.
Yeah.
So if there's a tie, there's a high probability that they are using the same UTXOs.
Yeah. Yeah. Because the first one is about West, right?
Yeah.
If the West is same, then chances are very high that the inputs are also same. Okay. Okay, cool. That was nice. This was like a really nice run through on the coin selection shenanigans of Bitcoin Core. And so we are at the end of our session, 1 hour in. And thank you, Anmol, for joining in and helping us with
Thanks,
so much
Anmol.
nice feedbacks. And see you again next time, same next week, same time with another PR. For then, happy learning. Bye bye.